All right, so good morning and welcome everybody to the pedagogical part of the workshop. So this morning it's our great pleasure to have Jaikumar here, and he's going to start with the first of his 3 lectures on classical and quantum information theory. Jaikumar, take
it. Good morning. So my name is Jaikumar Radhakrishnan. I'm a theoretical computer scientist. I'm grateful to the organizers for this opportunity to tell you about classical and quantum information theory as I understand it and maybe sometimes use as a theoretical computer scientist.
We are grateful to you.
No, thank you. So, most of what I say will probably be familiar to you in one form or another. It might even appear to be abuse of terminology which had better uses in physics. But so please feel free to interrupt and ask questions if something I'm saying is not clear. Or if you feel that it can be said better, yes, I'll try to say it again. And I'll be grateful to you for your faith in my true potential. So the plan today is to just tell you about 3 quantities. Yeah, I've been told to restrict myself to between these 2 lines, but I'll defy the organizers once and write down a little bit here. And then. So the plan is to just tell you about 3 things. So these are 3 quantities, very famous in classical information theory. And they, of course, have definitions which are familiar to you. But my plan today is to somehow say things in a way that these definitions emerge out of what you might call engineering problems or problems of communication. And then at some point, we will start studying these quantities for their own merit. So the problem is this. So you have a source, a probabilistic source X. And by a probabilistic source X, what do we mean? So you have some experiment, and it has n outcomes. And associated with each outcome is its corresponding probability. So when I write a source, you should think of, or when I say source, you should think of something like this, sometimes called a random variable. Okay, but everything will be discrete. The number of possibilities will be finite, and I will use the letter n for it. And this set A1 to AN will be called the alphabet of the source. So the source coding problem associated with this probabilistic source is the following. There are 2 parties. We imagine that Alice is the one who is performing this experiment, and she observes one of these outcomes, and she needs to transmit the outcome to Bob by means of bits. And in the end, Bob must know what Alice observed. So what do we do? To each outcome, we associate a string of zeros and ones. Okay. And the agreement between Alice and Bob right in the beginning. So Alice and Bob see this, and they are now trying to design an encoding. And the way they wish to design the encoding is, or the purpose of the encoding is, when Alice observes A1 in the lab, she transmits W1 over the channel. When it's AN, she transmits WN. These are all strings of, and I write star here because they are not fixed length strings. Different outcomes are assigned strings of different length. And what we wish to minimize is the amount of communication. How much does Alice need to send Bob? Okay. So over this minimization is over all choices. We would like to come up with the best encoding so that this quantity is as small as possible. Question?
If their lengths are different, then if you get a particular message, let's say it's length n, and depending upon the partition of n, the message vary as well.
Yeah, so I'll just, so no, valid question. So let me just repeat the question. I don't know if it's, so the question was, suppose there are code words which are 2 bits long, and then there are code words that are 10 bits long. Now, suppose Bob receives a message which is 50 bits long. Now, how does Bob go about breaking up that 50 into various things? If everything was of a fixed length, there would have been clear inter-symbol positions. But without that, there is that issue, and we will need to incorporate that in our minimization. Thank you. Yeah. So, question? Sorry. Yeah, so this is the length of the word. So, this is, yeah, so these are vertical lines. 001 is so it's like, yes, so the service provider charges you 1 rupee for each bit you transmit. And this is the expected cost you would incur to transmit this. But there's a restriction. These so this is encoding, which is this encoding should be prefix free. Now, this, this particular issue was already anticipated in that question. So what do I mean by the encoding is prefix free? These code words should be prefix free. That is, no code word should be a prefix of another. Okay, so what does that mean? So suppose I take W1 to be 001 and W2 to be 1. These are prefix free. Neither of the code words appears in the beginning of the other. Okay? But if I took so it could be that A2 had very low probability and Alice chooses to allot a longer code word for it, but A1 has high probability, and Alice chooses to assign a smaller code word. But when Bob receives, he wouldn't know whether to wait. Some additional bits are coming so that the eventual conclusion is that Alice sent A2, or whether Alice's transmission is over. So we would like our code words to be prefix free. That means none of these code words should be a prefix of the other. Okay. Question?
But wouldn't that mean that just by knowing a few bits, you should be able to distinguish which one it may be? There would be some similarities.
There would be some similarities. We will analyze that. But it doesn't mean that there is lots of redundancy. It's just because I have written only 2 of these encode words. There might have been other code words also. In that case, it is not true that by looking at just the first few, you would be able to tell everything. Okay, we'll see. Yeah.
Okay, so you're saying the full thing shouldn't come, like W1 in its
Yeah,
entirety?
so, sorry. So what did I mean? This part, yeah, W1 sits in the beginning of W2.
Okay.
Yeah, so it's a prefix of W2.
Okay.
So it should be prefix free, and ensuring that the code words are prefix free solves that problem, because when we see a big string, we start scanning from the left, and as soon as one of these code words appears, we know that it has ended. Yeah? And then we start parsing, so to say, again, and we keep making boundaries, and we are able to recover what Alice meant to say. All right. So now, if you have a set of strings and they are all prefix free, then if you look at 2 to the power minus wi, this should be less than or equal to 1. I mean, why am I doing this? I'm trying to solve or understand this optimization problem. But this optimization problem has to be understood under some constraints, and I'm trying to understand what the constraints are. There is a constraint which now I have formulated combinatorially in the language of prefix free. I would like to write an inequality so that that constraint starts looking like usual constraints in optimization problems, and then I can deal with that optimization. Okay, so it turns out that if the WIs are question.
Is this true for just minimum encoding or any encoding?
Any encoding, if you promise that the WIs are prefix free, this inequality will be true, and it's not a very deep inequality. I mean, it's called Kraft's inequality. And let me just explain. One way of visualizing strings in 0, 1, strings of 0, 1 is by means of a tree. So you have a root, and the left branch corresponds to 0, the right branch corresponds to 1, and this particular string 0, 0, 1 is 0, 0, 1. 1, 0, 1. So once you have a prefix-free set of code words, you can mark them on this tree. But what do we know? Because they are prefix-free, in any path from one of the code words to the root, another code word cannot appear, because then the code word on the top would be a prefix of this code word. then this inequality is obvious. Suppose you took a random walk from the root. This is a totally different probability. Yeah, this is a probability used to prove. You take a random walk from the root. What's the probability that you pass through Wi? If you started from the root, taking probability half left or right, what's the probability that you would go through Wi? Is it okay? And these are disjoint events. So their probabilities must add up to less than 1. Question?
Can this theorem be used as a definition of what it means to be prefix-free?
I was about to write that. Thank you. Yeah, this kind of talk is being constructed by the audience. So by the way, I'll go to that. Is the proof okay? Yeah. You suppose I took a walk from the top. I could not pass through 2 of them at the same time because they are prefix-free. So hence their probabilities must add up to less than 1. Converse, suppose you're given some numbers L1, L2 to Ln such that, yeah, so these are integers with the property that 2 to the minus Li is less than or equal to 1. Then there exists W1 to Wn such that the length of Wi is Li and Wi are prefix-free. That is to say, this is a necessary and sufficient condition. Yeah? That if a set is prefix-free, it satisfies this condition. If some numbers L1 to Ln satisfy this condition, then you can cook up objects on this tree. It's again not very hard to do for you. If the Li's satisfy this, then it's possible for you to arrange code words so that the ith code word has length Li, the specified length Li. Furthermore, these code words are all leaves on the tree. None of them is one above the other. Questions? Is that okay? So now, this optimization problem, instead of saying all this, yeah, we could just write the constraint yeah, it's not unique. It could be that, you could, for example, make the left tree the right tree. And as far as this objective function is concerned, it won't make a difference. Yeah? I'm assuming that zeros and ones cost the same. Yeah? Transmitting a 0 or transmitting a 1 cost the same. Yeah? So these WIs are not unique, but we are interested in this question. Okay, so we have a random variable, and we would like to know how much information is there in that random variable. And we are taking some sort of an operational attitude to information. Say, I don't know what this word information means, but I understand costs, and I would like to know, to transmit this X, what is my cost? And I would like to call that the information. So this is the object. Now, if you drop this integrality condition, that these Li's should actually be integers, which is what makes sense here, yeah, but allow them to be arbitrary real numbers under this constraint, and we try to minimize this, the optimum is in fact if you want to minimize this quantity subject to this constraint, turns out what you should take all the LIs to be, or each LI to be, is this. Okay, and we'll prove this. Okay. And if you did that, then what cost do you get? Yeah. So if I declare this problem, yeah, T of X to be the transmission cost and if you believe me that the optimal solution is this, and let us agree to call this H of X. So all logarithms for me, yeah, so are log to the base 2. Yeah, I'm a computer scientist. T of X is the optimum here if integer constraints are imposed. Without constraints, the optimum could only be smaller because it's a minimization problem. So, yeah. And if you LIs are these numbers, these are in general real numbers. If you just rounded them up, you see that this constraint is still satisfied. If the LIs are increased, no harm is done to the left-hand side. I mean, if anything, it becomes smaller. So these constraints are still satisfied. The converse tells us that we can get code words of the specified lengths, and then the optimum, each LI, whatever its value used to be before, will go up by at most 1 because of the rounding, and you will get it. The transmission cost, that is, Tx is the optimum of this problem with the integer constraints in there. H of X, as we have now realized, is the optimum of this problem without the integer constraints. And these two things differ by at most 1. Is that okay? Yeah. Now, so LIs here are real numbers, which are this. Let me define Li tilde to be is that okay? I don't know. This means the next integer, yeah, round up. Yeah. So this quantity used to be Li. This can be at most Li plus 1. Now these Li tildes satisfy this, because if you put log 1 over pi here, yeah, it will become summation pi. Probabilities add up to 1. Yeah. And these numbers are now slightly more than log 1 over pi, so this constraint will still be satisfied. And by the converse, we can come up with code words or a coding tree like this. And using that tree, if we reevaluate this with Li tilde here instead of Li, you will have a plus 1 for each one of them. And there is this expectation. So is that okay? Thank you. Yeah, please ask. So now I just want to tell you why the optimal solution is this. So, yeah, the solution I am declaring is this one. Yeah. So let's take the difference between. Yeah. Li, maybe I shouldn't use it. Somebody came up with a solution, and their solution is Li hat. And I would like to claim that this difference is at least 0. This would mean that this is the best, because every other solution which satisfies the constraint gives me cost which is more than the cost that I get. This is all I need to show. Okay, and yeah, so this is, so the left-hand side is Pi. Yeah, so this is some devious things we do. Is that okay? And this is minus and log is a concave function. There is a negative sign, and if you just apply Jensen's inequality, you get that this quantity is greater than. So this looks like the average of the logs, and I'm replacing it by the log of the averages. Yeah. Sorry, I don't know what I did, but. Yeah, so you probably can do this better from there. But anyway, what do we know about summation 2 to the minus Li? It is less than 1. Yeah, that means this quantity log is negative. That means the minus is positive. Okay. Sorry, I didn't explain it very well, but there is one application of Jensen's inequality. So, and in general, what you just saw here is that if you have two probability distributions, P and Q, and you compute this quantity, yeah, so roughly the same calculation shows you that this is greater than or equal to 0. And it's still, and this particular quantity, yeah, so what do I mean by Pi? Pi is the probability of I under this distribution, Qi is the probability of I under this distribution, and you look at this quantity. And this is called the relative entropy between P and Q, and this quantity is always greater than 0 for the same reason. Here you think of 2 to the minus Li's. They're less than or equal to 1, but when people are trying to optimize, you know that when they optimize, this equality will actually hold. So you think of 2 to the minus Li's as probabilities, and then what we just did corresponds to this inequality, and this says that the relative entropy is always greater than or equal to 0, which is Gibbs inequality. Okay, so we'll talk about relative entropy tomorrow. Okay, but we already see it showing up in our calculations. Questions? Okay, so now h of x, this, where did I write? Yeah. This is Shannon entropy of the source x or the random variable x. And we have now discovered that it has a certain operational relevance, that it is the optimum encoding or optimum length, expected length of encoding for the sources. in a prefix-free fashion so that decoding is not unpleasant. Questions? Now, I mean, all this is nice and but still, this formula can be applied to all kinds of things. And for example, if you have X, which is yes.
Suppose you fix the length, then
Yes.
you don't need this prefix free condition.
That's right.
So,
Or it would automatically be prefix free.
yeah.
Yeah.
So will that cost more?
Yes. Yeah. So suppose, suppose there was one particular occurrence which had very high probability, and all other occurrences had tiny probabilities. It would make sense for you to assign that special occurrence a code word this, and the others a bushy tree. So suppose this probability of A1 was, and the others was 0.1 divided by n minus 1. Okay. The cost now is essentially 1 most of the time, and for the rest, it's some large number, log n. So whereas if you had given all of them the same cost, then this would have been demoted, and you would have got a cost of some log n.
But suppose all of them are equal.
So it is, if all of them are equal probability, then you would require all of them to be assigned the same, the optimum would automatically assign all of them. What is the length that we are assigning? Li is log of 1 over pi. Pi's are 1 over n, so all the Li's would automatically become log n. So yeah, there is some intelligence in this optimum. It automatically figures out, but the point is, it doesn't say you will be inversely proportional to your probability. Inversely proportional to the log of the probability. And why log? Because your possibilities increase exponentially as the length increases. So there is a log to be negotiated with there. Question? Yeah, sorry. So yeah, thank you. Yeah, I mean that's the trend of today's talk. Yeah. Okay. So if X was a coin toss with probability half and half, then H of X is 1. Now, if X is a coin toss, sorry, my head and tails I call 0 and 1. Yeah. But suppose it was, just the formula. The formula tells me that, sorry. So it was 1/3. So yeah, come to your question. Suppose all that Alice wishes to transmit to Bob is the outcome of the morning coin toss of a cricket match. And if she will have to send 1 bit, and this whole optimization problem makes no sense. Okay. In all these cases, she'll probably end up sending 1 bit. Okay. But the formula seems to give me different numbers. The formula says 1 in this case, 0.919 in this case, and 0.811 in this case. Is there some way to make sense of this difference? Okay. And so that's what we are going to do now. So this particular theorem that the transmission cost is between h of x and h of x plus 1 is called Shannon's source coding theorem with variable code length, variable lengths for the code words. There is a version of Shannon's theorem with all code word lengths roughly the same, and that is the version that we are now moving towards. So suppose there was that source x and so the source now spits out x1, x2, xk. Each of them is generated according to some probability. Maybe this, maybe this, maybe this, or maybe something more general. Now, how many, so where do these sequences live? These sequences live in a space of and now there are different sequences, and different sequences might have different probabilities. But what do we know? If we pick a typical sequence, the number of symbols little a okay, this is some sort of a loose English statement. So this little a is a element of capital A. Okay, so it's one of the letters in the alphabet. And if I repeatedly draw samples from this and k is large, we would expect a to appear about k times p of a. And each symbol a, because there are only n symbols, finite number, all of them will have their typical behavior. So of all the sequences here, there are sequences that are probably very skewed, but most of the probability resides on this typical set. Sets, I'll describe what the typical set is, but your intuitive idea should be that sequences in which the letter A appears roughly as many times as its probability dictates. Yeah. Okay. So now, yeah, so let me. This n to the power k. Each xi comes from a set of size n. It's one of a1 to an. How many possibilities exist for x1 to xk? There are n possibilities for x1, n possibilities for x2, n possibilities for xk, and we have the cross product. So the number of possibilities is n to the power k. So this particular set, the outer boundary that I've drawn, that has size n to the power k. Yeah? But not all the strings here, yeah, have the same probability. Yeah? But some of the strings I have chosen to call typical, and I'll tell you what typical means. And the whole point of entropy is to focus on the typical sets, typical strings.
You're talking about ordered sequence, right?
Yes, ordered sequences.
So suppose each had equal probability.
Yes.
Then I would think that all sequences are equally probable.
Equally probable. Every sequence, all sequences are equally probable. Yes, yeah.
It's not that the ones which have probability
No. More probable and typical are different. Okay. So we will talk about these in an example. Let me put down the definition and then I will try to explain things. So I agree. What I have said so far is slightly vague, but there is a notion of typical which we tend to use in everyday language, and hopefully some of it will be reflected in the formal definition. So here is a sequence taken from this. Yeah. Now, and let sorry, it looks all very scary, but it's just a simple thing and you know it by another name. You fix a particular sequence of length k, ask how many A's appear in it, how many A1s appear in it, how many A2s appear in it, etc. This A is just as general A. Yeah. And you normalize. So this is what you call empirical distribution. You picked a sequence of length k and asked, how often did I see A? And that is the empirical distribution. And we say that X bar is if the empirical distribution doesn't differ from the true distribution. So if X bar was drawn from a source X whose probabilities were governed by P, and in the end in X bar, you observed A with this frequency or this probability, this empirical probability, then you look at their difference. So one of them was this probability distribution. This was the true distribution, but what showed up was, then you look at all these differences, take the absolute value, add them up. Okay. And if this quantity is less than epsilon, yeah, then we say that this X bar is P epsilon typical. It is epsilon typical up to epsilon with respect to the distribution P. Okay.
Here somehow you're forgetting the ordering.
Here we are forgetting the ordering in the sequence. Yeah. And this is called the type of X bar. Okay. Or the empirical distribution of X bar is called the type of X bar. How many A's does it have? How many A primes does it have? And so on. Okay. So we forget the order. We don't care where it appears. The limit of what? Limit, you probably meant k going to infinity. No, but that's all right. Yeah. K going to infinity. Yeah, so these numbers, as k going to go to infinity, will approach this. Okay, but we'll do limits, but at the moment we are just defining this. Yeah, so let me just catch my breath. So for the rest, let us just fix epsilon to be some small quantity. Let's say k to the minus 1. The following is true. That is, if you look at, yeah, okay, 1 second. So let me, so this is the set of all typical sequences. That is that shaded set that I had in mind. Okay, but let us see. Yeah, so let us go through some examples. Now, if your P is this, if your X is this, if this is the source, and its distribution is called P, yeah, then what are the typical sequences? Typical sequences are those sequences of zeros and ones of length K, which have roughly half 0 and half 1. Okay? Because the empirical distribution should be the same as the distribution from which we are, with which we are comparing. If X was this, we are looking at those sequences which have roughly 2/3 ones and 1/3 zeros. Okay.
Something that's typical.
Uh-huh.
Really near the actual distribution.
I mean, that is true. Yeah, so yeah, I'll come to that. Yeah, but I wanted to address a previous question. If I take X and I draw K samples from it, yeah, which is the most popular string? Which is the string, sorry? 1, 1, 1, 1, 1, 1. It has probability 2/3 to the power K. Yes, but is it typical? No. Okay. Yeah, so it is not true that the most popular strings are the typical strings, meaning individually. But turns out that most of the probability, so there are these strings like 1, 1, 1, 1, 1, which under this distribution, this kind of a misleading distribution, everything has the same probability. So don't look at this. This one. Okay. There are strings which have lots of ones. And the more ones you have, the better your probability. But they are not typical. And even though they individually have a lot of probability, there are not many of them. There is only one of them. Okay. So their probability really doesn't count. The probability that really counts is of the typical sequences. So if you look at this set, yeah, so this is a fact. You might call it the law of large numbers or whatever. Yeah. So the probability of the probability that is outside of these typical sequences is, as K becomes large, goes to 0. Okay, so most of the probability is here. Okay, so now with this, we would like.
Instead of finding it this way, I mean, why don't you can just say that we are trying to calculate the probability distribution for a sequence for getting the ordering.
Yes.
It will give the same method, right?
That is this, yes. Uh-huh. But then you will ask which sequence? Because for a different sequence, it gives a different probability distribution. And the point is that for most sequences, but most in terms of the probability itself, so it's a little self-referential, you generate sequences according to the probability distribution P, and for most sequences, if you look at the empirical probability, that will be close to the original probability. But the point is, yeah, so yeah, I don't have, yeah. What you're saying is exactly what I think I'm doing. So this is one fact, but furthermore, so if suppose X bar is typical, what is the probability that so I didn't say what xk was. So xxx drawn independently k times, a sequence generated by sampling from x k times, what is the probability that it would become x bar? Well, this symbol A appears how many times? If, yeah, I mean, this is an equality. The number of times A appears in this sequence is NA x bar, that's our definition. So number of times we get PA is this is the probability. And if x bar is typical, then this number looks like k times PA. And this quantity is starting to look like 2 to the power. You will do this calculation in your head. Little x, sorry, this, my font is not very good, but this little x bar is just a sequence. You should think of little x bar as x1, x2, xk, and it is one particular pattern of zeros and ones or a1s to an. This particular pattern has a probability, and that probability is precisely this. And if x bar happens to be typical, then its probability will be PA to the power k times PA. And if this PA you promote to the exponent, it will start looking like this up to some corrections.
When you say that x bar, including the ordering or without?
Including, so whenever I write x bar, it is ordering. When I write probabilities or empirical probabilities or n, then it is without ordering. X bar is with the ordering. I'm talking about sequence. When I use the word sequence, order matters. Whenever I use the word set, then the order doesn't matter. Okay. So if I fix a particular sequence x bar, okay. So let's see. So in other words, so let me leave it at this. There are corrections, but they are second order in the exponent. They are not order k. They will be like k to the 2/3 or something. So the probability is looking like this. So how many typical sequences are there? Let me draw my box here. This is a to the power k. Most of the probability is inside this set because that probability is going to 1. The probability outside is vanishing. Each point here has this probability. Up to some corrections, ignore them. Then how many of them are there? If the total pi to go around is 1, or 1 minus epsilon, or 1 minus delta, and each of them is consuming this much, then the number of thank you. So it turns out, so let's get back to these. Yeah. In this case, I will draw these boxes again and again. So this is for x, which is 0, 1 with probability half. All points are the same probability, 1 over 2 to the k. And if I want to capture, say, even 10% of the probability, I will have to pick 10% of the strings. That means 1/10 of 2 to the power k. These many strings I will have to capture if I want to grab a good part of the probability. Okay. If this was the distribution, yeah, then the size of this set is still 2 to the k. The outer boundary is still 2 to the power k. But the typical size, typical sequences, their number zero point so, and if it was the third one, it would be like 2 to the k times, I don't know, something like that. So even though from the transmission cost point of view, we did not really see much difference between this, which was the original distribution, original motivation for our entropy formula. Our formula seems to be measuring something else or something more interesting, especially when we start doing repeated sampling from the distribution. If the distribution is uniform, then if you want to capture, any amount, reasonable amount of the probability, the exponent here, the coefficient in front of k, will have to be 1. If it is uniform. If it is this distribution, 1/3, 2/3, then the coefficient in front of k is 0.919. If it is the other distribution, which is even more skewed, it is 0.811. So what's the point? You might have a probability distribution, and there might be some points which have 0 probability. And there are these points, let's say R of them, which have non-zero probability. And there was this set A, which had n elements. There were n elements in all. Now we would like to know, what is the information in this random variable? So we could say, oh, this is a set of size n, and as I take its product with itself, I consider its higher dimension analog, the size of the set grows as n to the power k. And you say, oh, that is at the rate at which things are growing. N to the power k, or since we like. Yeah, so if you want to capture all possibilities in principle, then you will need these many. Okay? But suppose you say, no, many of them have 0 probability. We shouldn't really count. Okay? Then, yeah. Support of the product distribution, that is growing at the rate R to the power k. Yeah. So, yeah, if you want the full measure, if you want like to capture everything fully, then you have to pick R to the power k. But no, suppose you want to capture only 90% of it, not 100%. Then it is not R to the power k. It is And whether you want 90%, 99.999%, or you want only 1%, the number of strings, I'm very sorry with this, number of strings you need to pick will be 2 to the power h of k with lower order corrections. Or if you take this number, divide by k, take its log and divide by k and take k to infinity, you will always get h of x. So in that sense, h of x is the content, yeah, really where is the mass, or how much content does the distribution have, okay? And this viewpoint explains these numbers, which the earlier viewpoint of transmission cost did not. There is no expectation. We just say that I have a particular, yeah, 1 second. So, sorry, I don't know why you say I'm doing expectation here. Suppose I take an interval of length 5. Then I build a box of length, each dimension 5. What does the volume become? Well, in 2 dimensions, it's 5 squared. And if I take a box in k dimensions, it grows as 5 to the power k. Yeah. So this number 5 had something that controlled the rate at which it grew. Suppose this was half, then the volume of the box would be shrinking to 1 over 2 to the power k. Yeah. Now the same thing I'm doing for probability. But in the discrete case, I have a probability distribution on n objects. Essentially, how many objects do I really have when I go k dimensions? The answer is 2 to the power k times entropy is the number of objects I really have. The others, some of them outside actually have higher probability than the ones you are picking in the typical set. But if you throw them away, their combined probability is going to go to 0. So the amount that I need to capture grows as 2 to the power k times the entropy. And that coefficient of k is entropy. That is one understanding of entropy.
That you are willing to make errors for a certain number as long as the fraction goes to 0.
Okay, so let us, yeah, so finally, yeah. So what is, just one moment. Anyway, so let me what is the size of the smallest set which captures at least 1 minus epsilon fraction of the total probability? And the theorem I'm just repeating myself. So, yeah. Now, what has this got to do with source coding? So Alice and Bob, they are back to the old game, but they don't want to do one experiment, they want to do a large number of experiments. Okay? And Alice will send the outcome of the experiment. Yeah? But outcome of k experiments, and she will look at all k experiments together and assign it a code word. Okay? Now, Alice and Bob look at the probability distribution and they agree that we will just ignore the non-typical sequences. Okay, so if the occurrence is not typical, I am not even interested in sending that occurrence. Okay. So they focus on this set S of typical sequences, and they try to get the smallest set so that their probability is at least 1 minus epsilon. That means they say, let us agree that if we fail with probability epsilon, then it's okay, but we would like our transmission to succeed with probability 1 minus epsilon. Okay. In that case, to convey the outcomes of k experiments, how many bits do they need? K times entropy. That is, per experiment, they have to send entropy number of bits. And when this number h of x is less than 1, it still makes sense. K is a large number, yeah? And to encode the outcome of k coin tosses, which are biased 1/3, 2/3, the number of bits that they need to send is not k, but only 0.919k. And that 0.919k is controlled by the entropy of the probability distribution. Is that okay? All right. So, yeah, after all this. So this is all I wanted to tell you about entropy from this point of view. Questions?
Did you maybe say that they will have to come up with a new coding scheme when they're sending k outcomes, or the old one will still work, like the tree that you drew?
So the old one was very kind of tailor made for strings of length, of multiple length. Here, what do? They take the typical set, and they know that the number of different strings in this typical set is 2 to the power k times h of x. These are the number of possibilities. Yeah. This number, to each of these strings, they just pick up a different string of length k times h of x and assign it. And that is the protocol between Alice and Bob.
I could also have used the previous coding and just use the variable length things.
Yes.
Because it's prefix free, I can still decode k of them, right? So
you will still be able to decode k of them, yes, sorry.
And the expected length of that transmission will be k times h of x.
That is true. If I use the previous one, and I could still do that, and then it would be variable length encoding, and there will be no error at all in that case, but we would only be able to say that the expected length is bounded by entropy per symbol. Here we are saying that the actual cost of transmitting k symbols is k times h of x. Yeah, and you cannot do any better, because suppose Alice said, no, this typical sequences and all that is just in discussion. I have this other set which also captures 1 minus delta of the probability, and this set is much smaller than this, so I can get away with fewer than this bit. No luck, because these typical sequences have 99% of the probability. So no matter what you do, you will have to capture a good fraction of these strings. And each of these strings roughly has the same probability. So the number of different possibilities that you will have to negotiate will roughly be this, no matter what you do. So, yeah.
But I guess from a practical point of view, maybe you don't know what k is ahead of time. Like maybe you want to send 100 times, maybe 1,000 times. Then the previous protocol makes more sense.
That's right. Yeah, that's correct. But in general, block coding, yeah, seeing many symbols and then assigning a code for them together is a good strategy, rather than trying to encode each of them separately and trying to concatenate their individual encodings. Okay, good.
Hello.
Question.
So our actual value will be t of x, right? So why we are working in h of x?
Sorry?
We want to calculate t of x, right?
No, we calculated t of x for that definition of t of x, yeah. But I wanted to motivate And from, okay, so let me just review what we did so far. We started with T of X for one shot communication. One occurrence in the lab, I want to transmit, okay? And while trying to optimize that, the number entropy showed up, yeah? And that entropy, we could also calculate for all these. And in these cases, T of X was always 1, but entropy was giving different numbers. No theorem was violated because there was a +1 somewhere, okay? Yeah. But then I wanted to understand, is h of x saying something useful? Anyway, even in these cases. And so I adopted this asymptotic view of looking at it. And the conclusion seems to be that h of x governs the rate of transmission when I'm allowed some small amount of error. And I use fixed length strings. Alternatively, it captures the rate of growth of the probability distribution in terms of where does the mass of the probability distribution reside, on how many distinct occurrences. So if this looks very much like engineering, what we call number and number of possibilities will become number of dimensions, and then you will all get excited when we start talking about quantum states. The calculations will be the same. Best transmission cost. So we wrote down the inequality. T of x is less than h of x, and in this case, we even said what the various lengths will be. They will look like, yeah. But it doesn't give T of x, it gives something perhaps slightly more than T of x. Okay. But is there an effective way of finding T of x? Yeah. It turns out that it can be done, and some of you who've seen an algorithms course. So there is a method for finding out the optimum value T of x using an algorithm, given the probabilities. Okay. But that doesn't take us very far. Okay. Somehow this asymptotic way of thinking about it is mathematically more fruitful, and so we'll see. Yes.
So each character,
Yes.
alphabet appears
Each character, yeah.
probability times total number n.
Yes. K, total number K.
Yeah, that is
Plus or minus epsilon. Yeah. So we don't say absolutely typical, because these probabilities, for all you know, could be irrational numbers. And there is no hope for a letter to appear exactly PA times K times. Okay. And K could be an odd number, and the probability could be some 1 over even number, and it could just not work out. Yeah.
So does it give any non-typical volume, like non-typical shape inside?
Yeah. So at the moment, although I have been drawing geometrical pictures, please don't take my pictures very seriously. The shape, I have not, these are A1, A2, AK, AN, they were listed from left to right, but we could have listed them in any permutation and it would have been the same. Yeah. So I don't know, I don't have anything useful to say about the shape at this point. Question?
Yeah, so to me it seems like we do a sampling problem to figure out a probability distribution.
Yes.
But then the answer of how to do the sampling already depends on the probability distribution through the entropy. I need to know the entropy to know how many times I need to sample.
No, I was given a probability. So yeah,
Okay,
so I was given a probability distribution, and I was told that this was the model for the experiment I'm going to perform in the lab. The various outcomes are going to come up with these probabilities, I've been told. But my collaborator is on the other end, and I need to transmit these outcomes, okay, so that we have a shared copy of the experimental data. The question is, how much how should I encode the occurrences in my lab so that I can reliably communicate? Yes, please. Yes. Yeah. So, I mean, these are questions that statisticians ask, and they have tests to determine if there is, I mean, whether things were drawn independently or not, of course. What does, yeah. So what I've done is the memory-less situation. That is, each time I ask the source for a new symbol, it generates it with the same probability. Yeah. Now, if I would like to know if the system has memory, for example, it could be that the system has a state. And when it is at a particular state, it emits symbols with some probability. Okay? And then after emitting, it moves to a different state. That would amount to the system having memory. Okay? And these are what are called hidden Markov models, where there is a Markov chain going on inside. And what we are seeing is an observation of the state which appears to us as symbols. Okay? And their distribution varies. Now, yeah, inferring the underlying mark, even assuming that it was a Markov model, yeah, is a kind of, yeah, is an important problem, but right now I don't know enough to tell you about it. But this is studied. Okay.
Sir, sir, am I audible? I had a question.
Just audible but not visible. Where?
Sir, I am online. I have joined online actually.
Oh, thank you. You're most welcome. Please, sir. Yeah.
Sir, so as you were saying, can we then say that the major interpretation of entropy would be how the sequence projects in higher dimensional spaces?
Not how the sequence projects in. So we don't, although we did a lot of discussion in terms of sequences, we are talking about the bulk. We say somebody has given us a probability distribution. Okay, set theorists talk about cardinality of a set. How many elements are there? Okay.
Yes.
Maybe probability theorists talk about support of their probability distribution. Okay, meaning how many things have non-zero probability. We are sort of doing something in between. Yeah? That is trying to pay more attention to the probabilities themselves, so that as the dimension grows, the amount that we need to focus on grows, but much less than either the support or the cardinality itself. So that's what we are focusing on.
Okay, sir. So just then one more question. You had said that suppose I fix the size of my string, that is say k, and also now I change the epsilon. So
Yes.
can I say that the major mass that is being decayed from the center of my typicality would go like exponential of my size of the set?
Yeah, so since we have taken logs and divided by k, the number doesn't change based on epsilon.
In here where we had taken actually the epsilon typicality, but
Yes.
suppose we had changed from epsilon 1 to epsilon 2 typicality, then
Yes.
we'll get a different typical set.
Correct.
Will that set be exponentially smaller than the other one?
Okay, so this was the typical set with
For
respect to one epsilon.
Yes.
This was the typical set with respect to a slightly bigger epsilon.
Yes, sir.
So the number of elements in this typical set will look like 2 to the power k times h of x something. There might be a lower order term, let's say k to the 2/3, and there will be some epsilon here. Okay, if you change this, this changes. The top stays the same. Okay, unless you make epsilon. So I assume you're thinking of epsilon as a constant. That is, first you tell me the epsilon, and then I get to change k. Okay, so if you fix any epsilon, you say 0.999, yeah, I will have to pick bigger sets. But in terms of number of sequences in the set, it will look like 2 to the power k times h of x plus some smaller things.
So so it will get epsilon compactified after some choice of
That's
epsilon.
right. If you take log divide by k, I don't know the meaning of compactified, but I assume you mean in the end, if you look at the rate at which the volume is increasing, by which I think reasonable people would say, what is the exponent in front of k? That doesn't depend on epsilon at all.
Okay, sir. Thank you.
So maybe, yeah, okay, so I had started writing my notes, so it will be on the website, but my notes are obviously not the best source. I will at the end tell you where I learned these from. Okay. So maybe, yeah. Good. So maybe this is, I have done only 1/3 of what I wanted to do, but that's all right. Yeah. Thank you very much for the question. And, so we will do this tomorrow, and I'll try to be more systematic. And but please keep your questions coming. Okay. So maybe I will tell you what conditional entropy is. Yeah. Is that okay? But yeah, please don't. Yeah. Yes. Question.
So what we have done till now is just from the operational point of view, right? Not from decoding point of view till now.
Yeah, so we have not decided. Yeah, so we have not figured out an efficient way of decoding. We say, look, in principle, a decoding is possible. Okay, but when you actually do things in the field, you would like encoding and decoding algorithms to be efficiently implementable on a computer, and they are being done on your mobile. But that is not what we are discussing. We are sort of taking the abstract view and trying to understand how much information is there in a probability distribution. Yeah. So is there a way to stop this? Okay, it will. Yeah, yeah. I can take 10 more minutes. Thank you. So yeah, please don't take my engineering concerns so seriously, but that is where this version of entropy came up. We tried to understand what is the information in a random variable. We said, well, information, I don't know what information is, but how much does it cost to transmit it? And then I got some numbers, and numbers stopped making sense. And I said, okay, let me try asymptotics. And then all the numbers started making sense. I'll leave it at that. Okay. So X takes values in a set A, Y takes values in a set B, and there is some so they have a joint law, and their behavior is governed by these numbers, which I will call PAB. Yeah. And So this is the conditional distribution of y given that x has taken the value a. Just notation at the moment. And so I will call it q of b because p is taken, and I'll for a. So when I just write p, it is referring to x. This, I hope, will never be confusing. And when I write q, I mean the marginal distribution of y. Okay. Now, so let's say x bar is p epsilon typical, okay, with respect to the marginal distribution. So when I now draw from a source like this, what I get is x1, y1, x2, y2, xk, yk. Yeah. I get these composite letters of the alphabet, and there are k of them, k such pairs, and I call this x bar, y bar. So x bar refers to the top row, y bar refers to the second row. Yeah. But of course, they were generated in a correlated fashion because they have a joint law. Okay. Assume that this part is typical. Okay. So now, for this composite source, we can again talk about typicality. That means the pair AB, yeah, the pair A on top, B should appear k times PAB times. Okay. So yeah, so if you think of this as a single source, there is a notion of typicality, and that we just inherit from our previous definition. Okay. But I'm trying to break it up in a different way. I'm trying to say that if the whole sequence is typical, then if you look at the top part, that would also be typical. Typical with respect to its own characteristics or its own law, which we call PA. So with respect to that. So fix one such typical sequence. And let us ask, so fix a typical sequence X bar, and we ask, yeah, how many Y bar are there such that X bar, Y bar, yeah, I'm writing them horizontally, but you should visualize it like this, is jointly typical. So we have fixed one typical sequence. That means the number of A's is P of A, number of A primes is P of A prime times K. Yeah. Number of ANs is P of AN times K. Now, X bar is fixed. How many Y bars can I place under them so that if I evaluate this composite object in terms of this law, it would look. So now if I restrict attention to the A's, just the positions where there are A's, yeah. No, I mean, if I'm picking things at random, And if they are jointly typical, X bar will have to be typical automatically. If the total number of pairs AB, for all pairs, all possibilities AB, if they are roughly appearing in proportion to their law, then if you look at a particular letter A, well, that A occurs accompanied by different B's. Yeah, but each of them is following the law. So A itself, even if I ignore B or trace out B or take marginal on A itself, it will come according to its proportion.
You're saying that A, B jointly, you're taking the vector to be typical, right?
Yes, according to this law.
And then you're saying, okay, so my X bar is typical.
Now the top part will also be typical according to this law.
So Y bar is also typical, right?
According to itself. But what does joint mean? Yeah, so just because, so suppose X and Y, yeah, suppose the distribution was that whenever X takes the value 0, Y takes the value 0. Okay, so a typical, jointly typical sequence on the top would, and suppose everything was 50-50 probability, would have zeros on the, half of the entries on the top would be zeros, half of the entries on the other half would be 1. Yes? That is to say that X is typical. Yeah, half of them 0. To say Y is typical says that the bottom row has zeros and ones of the same proportion. But to say that they are jointly typical according to this law is to say that most of the time when 0 appears on the top, 0 has to appear at the bottom, because otherwise the symbol 0, 0, which is supposed to have probability half, won't have probability half. Yeah. Yeah. So, but let me, yeah. So we have fixed our X bar, and let us focus on the positions where the letter A, yeah, it's hidden here, the letter A appears.
Hello.
Yeah, please go ahead.
Are B drawn from the same probability distribution? B also drawn from the same?
No, it's not independent. They have a joint probability distribution. So in fact, this could be zeros and ones, and B could be a set of colors. They don't even have the common set, perhaps. It's just some pair of random variables with some joint distribution. And the marginal on B has no relation to the marginal on A. In fact, it may not be even comparable because they're talking about different objects. Yeah, I mean, whether it is raining in Bangalore versus whether it is cloudy in Madras.
So how can we talk about what a typical distribution for B means when it does not have an independent probability distribution?
When you have a joint distribution, you do have probability Y equals B is summation over A. Yeah, so when you have a joint distribution, you have these two marginals. Sorry, my language probably is throwing you off. I mean, this is what you do all day. Yeah, yeah. When you have a joint distribution, there is a marginal distribution and marginal distribution. So I'm specifying the marginal joint distribution and inheriting the marginal distribution, and I'm taking a lot of time. Yeah, but
so you're saying that if the probability distribution is typical jointly, then it's also typical for them individually.
Yes.
But if you know that it's typical individually, that doesn't mean that it's typical.
Thank you.
That's
Yeah,
right.
I wish I could say it that clearly. Yeah, yeah. Now, but suppose we have an X bar which happens to be typical, and we are focusing on how many A's there are. Well, the number of A's here is k times, where P is the probability distribution for X. Yes. Now, if this sequence is to be jointly typical, then among these K, let's call this K prime, how many B's should appear? Yeah. Of these K primes, we should have seen, it should appear to us that the second row was drawn according to the conditional distribution. So that is K prime times Sorry, I'm saying things informally. I'll say it better next time. But I want to get to the point. So ignore this, project only onto these K prime locations. It looks like a problem that we started with. It is K prime samples drawn from distribution, from this distribution. How many choices do we have? 2 to the power K prime. This K prime is of course a function of A times the entropy of the distribution of Y given that X equals A. This is what those are the only interesting sequences. The rest of them have no probability. So if we ask how many jointly typical sequences do we have? Well, the number of ways to extend these coordinates is this number. Now focus on A prime. That would have a K prime of A prime, H of Y given X equals A prime. So what is the total number of ways to extend X so that the combined thing becomes jointly typical? It would be product over all A's in A, 2 to the power. The number of times this A appears, which is already K times P of A, times H of Y given X equals A. Yes. And if you rearrange this, this looks like K times summation over A, P of A, H of Y given X equals A. Please ask me if something is not clear. And this quantity is called the conditional entropy of Y given X. How many additional choices remain once I pick a typical sequence? For the typical sequence itself, there is an entropy number of choices. Entropy of its own distribution. After that, how many more choices do I have so that the combined thing starts looking typical? That number is governed by this number. It grows exponentially, but the coefficient in front of the exponent is the average of certain entropies. Yeah? That is called the conditional entropy of Y given X. It has its uses. Okay, so we'll talk about it next time. Yeah. Thank you for your patience. I'll come again. Questions?
Thank you, Jaikumar. Maybe 1 or 2 quick questions since we are running a bit late. Okay, there were a lot of questions during the lecture. So maybe questions can be postponed to the tea session. So let's thank Jaikumar again.